Okay, good afternoon, dear colleagues. My name is Dmitry Ledon, and I am pleased to present you my report. Laser shock peening is one of the promised methods of surface treatment of materials for the purpose of hardening. This method makes it possible to practically get rid of the effect of heating of the near surface layers, which is very important for materials which a unique structure due to the absence of recrystallization processes that level out the previous thermomechanical treatment. The shock wave actions initiated by short duration laser radiation of the order of nanoseconds is accompanied by structural phase transaction and change in the surface topography. This procedure allows obtaining unique physical and mechanical characteristics in narrow areas of the material, which increases the strength and structures and their resistance to fatigue failure. An untraceable effect that can occur during shock wave loading using a laser is spall fracture. This phenomenon can occur at a certain rate of laser power and structure size. The aim of this work is a numerical study of loading regimes using a laser. The numerical study corresponds to experimental scheme, which is present in the slide. Experimental studies were carried out in this article. The components are shown in the figure. Number 1, detectable equipment for fixing the specimen. Number 2, specimen. Number 3, laminar flow of water. Number 4, aluminum foil glued to the specimen. Number 5, laser impact zone. The problem was solved numerically in the axisymmetric formulation. The finite element method was used for the solution. Laser loading was simulated by setting a pressure pulse in the impact zone. The pressure pulse has a triangular shape. The pulse duration is 50 nanoseconds. 3 different pulse amplitudes are considered: 1, 10, and 50 GPAs, and 3 different barriers thickness are considered: 1, 0.3, and 0.1 millimeter. The complete system of differential equations for describing of the behavior of deformation and fracture of materials is as follows. It consists of the equation of motion, number 1, the equation of continuity, number 2, the kinematic relation, number 3, the constitutive relation, number 5, the kinetic equations for internal variables, number 7, 8, and 9, and the head equation, number 12. The destination of the parameters are present on the slide. The simulated options are present in the table. Only in one case there are no signs of spall fracture. It is marked in the light green color. In 5 cases, signs of spall fracture are observed, but spall does not occur. They are marked in green and blue color. The absence of spall in this situation is related to the geometry of problem, namely with the fact that the radius of the zone of influence is much less than the radius of the target. In the 2 cases considered, spall fracture occurs, and in one of the options the target is punched. The calculation for a pressure amplitude of 10 GPa's and barrier thickness of 1 millimeter is shown on this slide. The pressure distribution field is shown in the figure. It can be seen that signs of spall fracture are observed inside the specimen. However, macroscopically, it remains intact. A similar phenomenon is observed in the experiment. The image will be shown later. The calculation for pressure amplitude of 10 GPa's and barrier thickness 0.1 millimeter is shown on this slide. In this case, spall fracture occurs. Two characteristic types of loaded specimens are shown in this slide. The results were obtained by the authors of this article. In one case, signs of spall fracture are visible, left one. In the other case, spall fracture is absent, right one. The velocity profiles of the free surface in the calculation on the left and in the experiment on the right are shown in the figure. Qualitative conformity is observed. To obtain a quantitative agreement, it is necessary to know the loading pulse in the experiment. At the moment, it has not been measured in the experiments performed. This is one of the possible ways to develop the work. And conclusions. Loading regimes that lead or do not lead to spall fracture during laser shock peening are qualitatively determined. A number of situations observed in experiments are qualitatively described. Thank you for your attention.